Hello everyone. This will be our lecture for lipids. It's quite long, but I will try to abbreviate it. Tapos, you guys will just have to pause on the screen if you need to digest some of the things, like the tables that I will be showing. Okay? So for this lecture, these are our learning points. I'm sorry if you can hear the rain. So first up, let's look at an overview of lipids. So lipids do not actually have a common structural feature. Like for example, our carbohydrates, our proteins, they have some sort of common structural feature to them. Diba yung proteins, NCC, sunod-sunod, and then our carbohydrates are always a chain of carbons, and then we can write them in their Hayworth or Fisher na notation. But for our lipids, they do not have that. Although all of them are relatively insoluble in water, but are soluble in non-polar solvents. The main groups that we'll be talking about are the fatty acids, so saturated versus unsaturated, glycerides, those with glycerol, non-glyceride na lipids, and the complex lipids. Our lipids can be broken down into these several groups that we talked about a while ago. You can also break them down this way, where we have the simple lipids, the compound lipids, which have other groups like phosphate groups or sulfur groups, and the derived lipids, which come from other lipid backbones. We can also group them according to whether or not they have fatty acids. So our waxes, fats, and oils, so our simple lipids, all have fatty acids, phospholipids and sphingolipids as well. While those without fatty acids are usually the ones with a steroid backbone, which we'll be talking about again later. There are several functions of your lipids. First is for energy storage. So we don't just store and get energy from our carbohydrates. Our lipids are actually a very excellent storage for energy. In fact, each lipid molecule, actually fats, you can have 9 kilocalories of energy, while for your glucose, your carbohydrates, you can actually get only 4. Proteins as well, you only get 4 kilocalories. Okay, so they're actually very, very good sources of energy. But I'll tell you why they're not our main source of energy for day-to-day life. Another function is we see them in our membranes. Remember our phospholipid bilayer? So that's our membranes. We find them there. They're also for emulsification of the fats that we digest in the form of bile. Our lipids, because they are steroids, are also lipids. They can act as messengers as well, like your arachidonic acids, prostaglandins. They are messengers na messenger lipids, and we'll see later our steroids are also messenger lipids. They're also protective, so anywhere that you find fat accumulations in your body, they are there because it's protecting parts of our body that need extra help. So, for example, in your gluteal area, there's a fat reserve there, diba? Our butts are quite fat for most people. That's because it needs that cushioning for us to be able to sit down for longer periods of time. If we did not have that fat pad, it would hurt a lot to sit down. And lastly, they are also for insulation. So other than our fats helping us be insulated when we're adults, it is actually very, very important for babies, yung brown adipose tissue. A lot of babies have that because newborns especially are not very good yet at regulating their body temperature. So they have that brown adipose tissue to help them be warm in the outside world. So let's talk about fatty acids first, which a lot of our lipids have. So fatty acids are just naturally occurring monocarboxylic acids, which mean they have a carboxyl group here and they have a hydrocarbon chain. Typically, they are unbranched, about 12 to 18 carbons long, and usually they're in even numbers. They're for transport and storage of energy. And the longer the chain you have, the lesser the solubility in water and the greater the melting point and the surface area. Because remember this hydrocarbon chain, if this is much longer, this is already nonpolar. So if it's much longer, it's going to be even more nonpolar. Therefore, it's going to be less soluble in water. We can classify our fatty acids in different ways, and the first way is just by the length of your chain. Short chain fatty acids are those that have fewer than 6 carbons. Medium chain fatty acids are those 6 to 10 carbons long. And long chain fatty acids are those that have 12 or more carbons in their chain. So, yun lang. Just remember the number 6, 10, and 12. We can also classify our fatty acids by the degree of saturation, meaning how saturated are the bonds. In my head, it's usually how saturated is it with hydrogens. It is saturated if all of your carbons have their hydrogens bonded to them. It is unsaturated if at least one of those lose their hydrogens and they gain a double bond instead of the hydrogens. Okay, so that's what happens. Your unsaturated fatty acids can be cis or trans. The cis fatty acids are those unsaturated ones where the remaining hydrogens go to the same side and they will result in something bent this way. It's very bent. While the trans fatty acids are those that are in opposite sides. So isipin nyo na lang transferred. So one is pointing up and the other is pointing down, resulting in a not so bent form. So instead of this one, a very bent, here it's just slightly bent. And if you've ever heard of trans fats, they are actually the fats that you want to avoid because they lower your good cholesterol or your HDL and increases the levels of all the bad cholesterol in your body. In nature, actually, they occur much less. Hence, a lot of the trans fatty acids that we have are actually because we manufacture them. We artificially produce them by partial hydrogenation. So, we hydrogenated some of our fatty acids, and then they became trans fats. So you'll find your trans fatty acids in a lot of the yummy food, like a lot of our fast food that uses vegetable oils and margarine. We see it in butter and milky products, so you'll also see it in chips and crisps and anything fried, actually, and a lot of other processed foods. So you should consume no more than 1% of your total calories for the day from trans fatty acids because the body does not need these trans fatty acids and they just accumulate. So that's very scary. Don't eat a lot of these processed foods. The last way to classify fatty acids, the second to the last is by the location of the double bond. So, di ba kanina we have our unsaturated fatty acids. And these unsaturated fatty acids can have the double bond at different positions. So, very good examples are your omega-3 fatty acids, which I'm sure you guys have heard of, and the omega-6 fatty acids, like your linoleic acid and arachidonic acid, which is a precursor of a lot of our eicosanoids, your arachidonic acid. So fatty acids, the double bonds before the ninth carbon are actually essential. And I'll tell you guys which is the ninth carbon ba. Okay, so let's talk about that in the next slide. We have several notations for naming our unsaturated fatty acids. The first one is by the delta notation, where we count our carbon 1 starting at the carboxyl group, here at the end, this one, yung may OOH. You count it 1, 2, 3, etc., until the methyl group. Okay? So the first number will be the number of carbons, then colon, and then The 1 here is the number of double bonds. So if you have 2 double bonds, you'll write there 2. And then you write the delta symbol, which is a triangle. And then the location of the double bond for where it started. So you would write 9, hindi 10 ha. Where the double bond started, you write that. For example, you have it also here sa 4 and 5. You would write 4, comma 9. Okay? But for us, the usual notation that we do is actually the omega. Kaya ito may omega 3, omega 6. Instead of counting from the carboxyl group, we actually count starting from the methyl end. So from here, we start 1, 2, 3, so on and so forth until the 18th. Ito, it just so happened that 18 divided by 2 is just 9. So, same lang siya na 9 pa rin. So, same thing. The first number is the number of carbons. So, if the number of carbons was just 12, this would be 12. Colon, then how many double bonds? The omega symbol, which looks like a curly W. And then dash, the number or the location of the double bond, which is still 9. Okay, so that's how we will name it. And that's how we got omega 3 and omega 6. We can also classify or just name our fatty acids by their common name. We have the omega name right here and their common name. So if the double bond is at the if it has no double bonds and it has 4 carbons, it is butyric acid. And if it has 12 carbons, lauric, 14 myristic, etc., etc. Okay? So how about here? What if it's 20, then 4 and minus 6? Okay, so it means it has 20 carbons and then it has 4 double bonds and it is at every sixth. Okay, it is at every sixth. That's your arachidonic acid. These fatty acids can undergo several chemical reactions which allow for it to be active in the body. So first you have esterification, acid hydrolysis, saponification, reactions as well at the double bond, which are your hydrogenation and partial hydrogenation. First up, we have esterification. And this is when a fatty acid reacts with alcohols to form esters. That's why it's esterification because you're making an ester and a water in the process because you combine these and release the water. Esterification is actually used a lot for creating some products that we use in perfumes, essential oils, cosmetics, and even flavorings. So, for example, this is quite interesting to me because I like perfumes. Here are the table of esters where this is the carboxylic acid here and this is the alcohol that it comes from. So for example, if it's methyl butanoate, it would smell like a pineapple. If it's benzyl methanoate, it might smell like peaches. If it's this one, butyl heptanoate, it might smell like coconut. And the ones here, semi-cinnamate, pag ethyl cinnamate, it will smell like cinnamon. So this is quite cool. These are not the only things that we use in perfumes, but it's nice to know that these esters, which are the esterification of our fatty acids, can actually produce these kinds of smells that we use in daily life. Next, we have acid hydrolysis. And from hydrolysis just means the breaking down of something into its separate groups with the use of water. And in this case, we get our water from the acid. So acid hydrolysis actually produces 3 fatty acids and glycerol from the esters. And it is the reverse of our esterification because in esterification, we put these together. And in acid hydrolysis, we break it down. So if you have a triglyceride here, which we have a glycerol backbone, this one, the 3 carbons, and then meron dapat dito OH, 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 and then each of those will have a fatty acid chain. That's why it's triglyceride. When we do acid hydrolysis, you release the glycerol and then the 3 fatty acids. Okay. The acids that we make use of to do this are your hydrochloric acid, sulfuric acid, and lipase, which is the enzyme in the body. Next, we have saponification, and this is just alkaline hydrolysis. So instead of using a strong acid, here we use a strong base, usually sodium hydroxide. And this is actually what happens when we make our soap. So it is the hydrolysis of an ester with a strong base. I'm sorry for this typo. And the product is an ionized salt, which is soap. Okay, so I don't know if you guys have ever made soap, but we typically have this one lye, and then this actually doesn't have a smell, the resulting soap. What gets the smell is you adding essential oils. Okay, so, and lastly, we have the reactions at the double bonds. That's what DB means. DB means double. And we have hydrogenation. It can either be complete hydrogenation or just hydrogenation and partial hydrogenation. So our complete hydrogenation is when we add back the hydrogens to the unsaturated or double bonded groups. Kaya siya hydrogenation because you added back the hydrogen. Partial hydrogenation naman is when you don't put back all of the hydrogen, just some of it. Okay, so ayan, it's still unsaturated in the end. So why do we do this? When you have straight chains of this one, of a saturated na fatty acid, it's very easy for them to stack with each other. That's why our phospholipid bilayer is easily stackable. But remember, if you have kinks there, pag meron kang cholesterol, like may cholesterol sa ating phospholipid bilayer, they remain liquid. That's because these chains can no longer stack easily with each other, which makes sense now that if we have unsaturations here, unsaturated na fatty acids, they will kink and they can no longer easily stack up with one another and they will become solids. So, and they will become liquids. Okay. They will become liquids if they can't stack with each other. Since sometimes we want vegetable oils to be solidified, we want them in this saturated form so they can easily stack up with each other and become solids. So margarine, for example, comes from vegetable oil, which was hydrogenated to be your stick of margarine, which is solid or semi-solid. Okay. Now let's move on to our simple lipids. Simple lipids are composed mostly of your fats and waxes. Your fats are just esters of fatty acids with glycerol, so like your triglyceride. And waxes are esters of fatty acids with other higher alcohols other than glycerol. So hindi lang yung 3 carbons with OH sa sides. Waxes can become fats and they're called fats are triglycerides usually, and cholesterol is more of a wax. So fats, as I mentioned, carry more energy per carbon due to being more reduced. Okay? And they carry less water per gram due to being nonpolar. And they're very good as long-term energy storage, but they have slower delivery. So ito na yung explanation ko. When we are at rest, fatty acids are actually a very good source of energy because you have a lot of oxygen kasi aerobic lang. Pag hindi aerobic yung conditions, fatty acids cannot be used as an energy source. So we go to glucose in the anaerobic processes. Okay, usually when we have high intensity activity because you need a lot more energy than your body can take oxygen in. So naga-anaerobic tayo dito. However, if you can see here, konti lang si glucose. But because the effects of glucose when they stay too long in your body in a short period of time is much more toxic. Glucose is more toxic than our fatty acids when they accumulate in the body for a short period of time. They are used up first. Okay? Para hindi tayo mag-diabetic ketoacidosis or a similar thing. So, hindi tayo hyperglycemia. Now let's move to our glyceride lipids like our triglyceride. So those containing glycerol. Lip your glycerides are lipid esters that contain the glycerol molecule, as I mentioned, and the fatty acid chains. These one, glycerol and fatty acids. We have two classes, your neutral glycerides, which are non-ionic and non-polar, and the phosphoglycerides, which are polar because they now have a glycerol plus a fatty acid plus a phosphoric acid with an amino alcohol. So here, this one. Your neutral glycerides are produced after the esterification of glycerol with a fatty acid. So they can be monoglycerides or just one fatty acid with the glycerol backbone, diglyceride if it's 2, and triglyceride if it's 3. And this triglyceride is actually the most important and the main storage form of these glycerides in the body. They readily stack with one another because I mentioned, diba, these are all saturated, so easy for them to stack up. And they constitute the majority of the lipids stored in your adipocytes or your fat cells, and their primary function is for energy storage. Your triglycerides, because they're the main star, we'll talk about them. They are glycerol plus 3 fatty acids. They're connected by an ester bond. As I mentioned, the energy that you get from these triglycerides is actually 9 kilocalories per gram. They're also for insulation and protection. They're good as carriers for the fat soluble vitamins, which are vitamin A, D, E, and K, and they're actually very tasty. Okay, fat is flavor. I think I've mentioned this before. Fat is flavor. Sources of our triglycerides are fats and oils, and your omega-3 fatty acid foods and omega-6 fatty acid foods. Omega-3, just like the ones you find in your salmon, in your tuna, and other fatty fish. So fats are just triacylglycerol mixtures that are solid or semi-solid at room temperature. Okay, so they're solid. They have a high ratio of long-chain saturated fatty acids, and these fats we get mostly from animals. So animal fat, like our butter. That's why butter in itself is actually solid. Okay. On the other hand, oils are those that are liquid at room temperature, and they have a high ratio of unsaturated to saturated fatty acids. That's why they remain liquid. Examples are oils that come from vegetables like our canola oils. Okay. Margarine is also coming from an oil which we just hydrogenated to become more like butter. So that's the one. Moving on to our polar glycerides, we have our phosphoglycerides first, which are the most abundant in our membrane lipids, and they're derived from glycerol 3 phosphate or G3P. So G3P before was your glycerol here, and then you have 3 phosphates attached to it. That is G3P. They contain acyl groups from long-chain fatty acids at the carbon 11 and carbon 2 of your glyceraldehyde 3 phosphate. Glycerol 3 phosphate. At the carbon 3, the phosphoryl group here is joined to the glycerol by a phosphodiester bond. Okay, so from here, it's connected here to the glycerol. Glyceraldehyde 3 phosphate. Ito, G3P. Next, we have our phospholipids, which I know you are very familiar with. The phospholipids have a structure wherein you have glycerol and 2 fatty acids plus phosphates, kaya siya phospholipid. They function for the cell membrane, lipid transport, and as emulsifiers as well, like if they act as detergents. Sources are egg yolks, liver, soybean, and peanuts. Okay, so obviously, you have a hydrophilic head, which is the phosphate area, and then the fatty acid chain tails are the hydrophobic ones. these hydrophobic tails will accumulate with each other, they'll face each other. So they can be protected from the watery environment of the body. An example of a phospholipid that we see is also phosphatidylcholine, otherwise known as lecithin. And this is a glycerophosphatide or a glycerophospholipid. It is amphipathic, meaning it has a amphipathic, which means that it has a polar head and a non-polar tail. So here clearly this is polar and this is non-polar. It acts similar to soap and detergents, where the soap will trap the non-polar germs or non-polar dirt with its non-polar tails, and then the polar heads will be facing outside, and then they'll form micelles. They are components still of cell membranes, and they are the major phospholipid in pulmonary surfactant. Your pulmonary surfactant actually helps with your breathing, and if babies do not have this, they will not be able to breathe properly with the first time that they take in air. Pag wala silang pulmonary surfactant, their lungs cannot expand and come back together after. They are also used as emulsifying agents in ice cream, and you'll also find them in egg yolks. That's why ice cream actually uses eggs. A real ice cream uses eggs. Another is our cephalin, which is phosphatidylethanolamine, and they have an amine group bonded to the phosphoryl group. So this is your ethanolamine here. They act like chaperones to help membrane proteins correctly fold to their tertiary structures, and they are found in high concentrations in the brain, but also you might find them in the heart and liver tissues. Next, we have phosphatidylserine, and their key role is in cell signaling for apoptosis. So they are like a signal for cell death. And they're key in the maintenance of cellular function, because if your cell is already malfunctioning, it needs to have that signal to be programmed to die. And you will find it in greatest concentration in the myelin in your brain or in your central nervous system. So if you remember your serine, diba, that is an amino acid, and this is it here, a phosphatidylserine, phosphatidylserine. Now let's move on to our non-glyceride lipids. First, we have our sphingolipids, and they're otherwise known as sphingophospholipids because they have a phosphate, and they are not derived from glycerol. Instead, they have a sphingosine backbone. So this is glycerol that we've been seeing kanina na, and this is sphingosine instead. You have a double bond here with a carbon, and then you have an amine group also, and an OH here. Your sphingosines look like this. So you have your sphingosine backbone, a fatty acid with an amide linkage, and you have ester linkages between your phosphate and the type of alcohol that it has. First, and one of the most important sphingolipids that we have is sphingomyelin, and it is a sphingolipid esterified to choline. So here's your sphingosine backbone. You have our fatty acids here, and your phosphocholine here, phosphate, and the choline, which is an alcohol. Your sphingomyelin is found throughout your body, and it is a very important structural lipid that we see in the nerve cell membrane, so in your neurons. It's also seen in the myelin sheath and helps insulate the cells of your central nervous system so that they can do saltatory conduction, and therefore the action potentials can be relayed to different neurons at a much faster rate. Next, we have our sphingoglycolipids. So instead of it having a phosphate group, it now has a glyco or a carbohydrate group. It has both a fatty acid and the carbohydrate component attached to sphingosine, and you have a ceramide backbone structure. It includes your cerebrosides, sulfatides, globosides, and gangliosides. And it's actually what determines our blood groups. And our blood groups are determined by what type of sugar is seen here with the glycosidic linkage. So your cerebrosides are the simplest of our sphingoglycolipids, and this sugar can either be a glucose or a galactose. And the most complex are your gangliosides. Here we have glucose, galactose, galactose. And then this one, if you remember, your GM1 is actually involved in Tay-Sachs disease. If you remember this, diba? That's one of our storage diseases, lysosomal storage diseases. Your gangliosides are chiefly found in the brain, which is why, if you remember from Tay-Sachs disease, you will have mental retardation or there will be mental disturbances when you have Tay-Sachs disease because of this GM1 ganglioside accumulation. Your cerebrosides, as I mentioned, they can either have a galactose here or a glucose that's attached to them. So this is your galactose and your glucose. Now let's look at our derived non-glyceride lipids. So if you need to pause and go back to the other ones and read your book as we go along, you can pause and everything. You can do that. Okay? For those that I'm showing this video to in the classroom, you can just still watch it in Quipper later. So first up, we have our steroids, and your steroids are grouped together because they have a steroid skeleton that looks like this. You have 3 hexagons or hexagonal rings and 1 pentagonal ring. They have no fatty acids and are non-saponifiable because they have no fatty acids. Because you remember, your saponification is when you release the 3 fatty acids from the glycerol backbone. Since they do not have a glycerol backbone and they do not have fatty acids, therefore they cannot be saponified. Your steroids include sterols, your bile acids and salts, hormones, I'm sorry again for this typo, and some of our vitamins. We have your isoprenoid lipids, which are built from 1 or more 5 carbon units called isoprene, which look like this. So steroids are isoprenoid lipids. And we also have terpenes, which are also synthesized from isoprene units. But let's focus on our steroids. Cholesterol is a very important steroid in your body, and they're amphipathic. Okay? Their hydroxyl group is what makes them polar. So remember, this is your backbone and this is your hydroxyl group. They are readily soluble in the hydrophobic region of the membranes, and they're interspersed in between your phospholipids to maintain the fluidity of your membrane. They are not readily catabolized by the body and is therefore not a good source of energy. So, ano ulit yung source of energy na lipid? Diba? It's your triglycerides. How many kilocalories of energy per gram? 9. Very good. If you answered 9. The functions of your cholesterol are as follows. You already know they are for the maintenance of fluidity and the integrity of your cell membrane. They also assist in manufacturing bile acids because they are the precursor of your bile acids. They're also for the formation of the myelin sheath, maintenance of body temperature, and the protection of our internal organs. Your cholesterol can also exist as a cholesterol ester or a cholesterol ester. Their hydroxyl group is conjugated by an ester bond to a fatty acid. Okay, so to this one, your hydroxyl group, na-connect siya to a fatty acid. Because of this, they have no more polar groups because they lost the hydroxyl group and are therefore very, very hydrophobic. And because of that nature, they are the preferred transport and storage forms of your cholesterol. Bile salts and bile acids are also steroids. They're amphipathic derivatives of cholesterol, so they're also still polar. And they're the primary component of bile. You have your cholate or cholic acid and chenodeoxycholate or your chenodeoxycholic acid. Your bile, remember, it's produced by your liver, but it is stored in your gallbladder. So it just goes down through the common bile duct and then goes here to the gallbladder to be stored for usage later on. Your bile acids are emulsifying agents. That just means that they're able to take non-polar na materials and then emulsify them, meaning they will make those non-polar particles into colloidal particles so they can exist within an aqueous or a polar solution. Okay. They also help with the digestion of fats in our bodies because they are emulsifying agents, and they help in absorbing fat-soluble vitamins. Again, these are your vitamins A, vitamin D, vitamin E, and vitamin K, or ADEK. So ito yung sinabi ko sa inyo na they help with the manufacturing of bile because your chenodeoxycholic acid and your cholic acid come from your cholesterol. Steroid hormones obviously are also hormones, and hormones are just messengers for signals in the body. They are cholesterol derived still. So if you eat a lot of cholesterol rich foods, that's why you might have a lot of these hormones. Sex hormones are those that control reproduction and secondary sex characteristics like your testosterone and estrogens. Your adrenal hormones naman control sodium balance and glucose metabolism, just like your cortisol and aldosterone. So here are the examples. At the top, your cortisol, corticosterone, and aldosterone. These are all adrenal hormones and they are for sodium and glucose maintenance in the body. While your progesterone, estradiol, and testosterone are all sex hormones. Your progesterone is the chief hormone, progestins. They're chief hormones for pregnancy. Pregosterone, ganun lang, pregosterone. Your estradiol is the main reproductive estrogen. So during the reproductive years of a woman, the main estrogen that she will produce is estradiol from the ovaries. While your testosterone naman is the main male sex hormone. Waxes, do not forget, they are still lipids and they're derived from many, many different sources. And they do not have a glycerol backbone, but they are, remember, they are still simple lipids. Lanolin is actually a type of wax that is a protective coating for our hair and skin, so it's naturally produced by our body. And they are just long chains of hydrocarbon tails with esters made of an alcohol chain and a fatty acid chain. So fatty acid, ito, and an alcohol chain, this one. And they're linked by esterification or ester linkage. And these waxes are solid at room temperature, like your candle wax, which is paraffin, etc. That's why if you also notice, your waxes are slippery because, diba, when you rub your candles, they're quite slippery. That's because they're hydrophobic, because they are lipids. Now to the last part of our lecture, our complex lipids. And these are very, very medically relevant. And you as medtech students and as medtechs in the future or future doctors even have to be very familiar with these complex lipids. Your lipoproteins are complex lipids because they consist of a core of hydrophobic lipids. So here we have our nonpolar lipid core with triacylglycerides, cholesterol esters, etc. Surrounded by amphipathic proteins. So here we have apoproteins, phospholipids, phospholipid layer, and cholesterol, as well as and this makes them apolipoproteins. Okay, so you have your cholesterol also here around. Typically, your lipoproteins are spherical. So they look like this with a filling in the center and then a coating, and are about 10 to 1200 nanometers in size. So that is their diameter, 10 to 1200 nanometers. So these apolipoproteins are located on the surface of your lipoprotein particles, these one. They help maintain the structural integrity of the lipoproteins, and they serve as ligands for cell receptors, meaning that is what your cell receptors will look for and that what they will attach to. That is what a ligand means. Your activators and inhibitors of enzymes that modify lipoprotein particles are the apolipoproteins. We have different types of apolipoproteins in the body. We have ApoA1, ApoA4, ApoB, C, D, E, etc. Okay, meron nga ring H, pero this is not as relevant as the others. And you can pause and take a screenshot of this table for you to be able to be familiarized with it. Okay. But basically, ApoA1 is the major protein of your HDL. So ApoA you find in your HDL, while your ApoB and ApoC you will find in the others. Okay, ApoB mainly yung mga low density lipoproteins, very low density lipoproteins, chylomicrons, etc. These low density, very low, high density were named so because of the separation of these cholesterols. So they're all cholesterols. They were separated after centrifugation, and it was found that your high density lipoproteins are highly dense, so they settled down, while your chylomicrons are the ones that went up, and they are the ones with the lowest density. The trend is that the larger the molecule is, the larger your lipoprotein, the less dense it's going to be. While the smaller it is, meaning your HDL is the smallest, it is the densest, meaning it's packing a lot in a very small package. First up, let's look at the biggest one, your chylomicrons, which contain ApoB4, and they readily float to the top of stored plasma to form a creamy layer. This one. It is what's responsible actually if you get your blood from patients na kakakain lang postprandial, you will see this creamy layer on top, and your chylomicrons are the ones responsible for that. Because remember, they are the ones that are very low density. They're the least dense of all of our lipoproteins, so they will float on top and form this creamy layer. Your chylomicrons are produced by your intestine and packaged with dietary lipids, and they deliver the dietary lipids to hepatic and peripheral cells. Okay. Your very low density lipoprotein naman, or VLDL, is the one next. They contain ApoB100, ApoE, and ApoC, and you'll see it here, ApoE, B, and C. Meron din silang konting ApoA. Okay. They're produced in the liver and are rich in triacylglycerols in the center. And these are the lipids, the lipoproteins that readily reflect light. They are major carriers of our endogenous triglycerides, and they transfer your triacylglycerols from the liver to the peripheral tissues. The low-density lipoprotein naman is significantly smaller than your VLDL and chylomicrons. Remember, as I said, the larger the molecule, the less dense it is. The smaller it is, the more dense. So ito, it's denser but smaller than your VLDL and chylomicrons. These LDLs infiltrate into the extracellular space of your vessel wall. So they go into the extracellular space where they become oxidized, and then the macrophages eat them. Once your macrophages are filled up with these LDL droplets, they form foam cells in this process. So you can see your monocyte is a type of macrophage. It differentiates, and then once your LDL comes into um, the extracellular space, it becomes oxidized, and your macrophages take them in to form these foam cells. These foam cells are quite dangerous if you have a lot of these excess cholesterol kasi they are pro-inflammatory. Meaning, pag marami tong foam cells na to, maraming inflammation na random na pwedeng mangyari sa body mo. And that's not good. The last and the the smallest and the most dense of all of them is your HDL. And your HDL is actually the only good cholesterol. They are synthesized by both your liver and intestine, and they can be disc-shaped or discoid or spherical. Your HDL is good cholesterol because it regulates your LDL storage and promotes excretion of these cholesterol. Kasi it is what takes back your LDL or your cholesterol from the bloodstream to your liver. Kaya ka hindi nagkaka-plaques na ganito na LDL accumulation. In comparison, the rest of your cholesterol, your LDL, VLDL, they're quite bad because they are the ones that deliver your lipids into the peripheral tissues. Okay, so you don't want that. You want it to be regulated with HDL. So if nakita nyo sa mga lipid profile na mataas yung HDL, that's actually quite good. So again, as I said, it can be in disc shape or in spherical form. The discoidal HDL has two molecules of ApoA1. This one, you have your discoidal or disc shape, and they represent the newly secreted HDL from your liver or intestines, and they are the most active form. However, once they accumulate more triacylglycerols, more cholesterol into their core, they become more spherical and they transform into the spherical HDL. The spherical HDL is actually the predominant form in plasma. Okay, so this one, the discoidal, is the most active kasi may space pa siya to take in these cholesterol, these triacylglycerols. But the spherical HDL, since sila yung na-transform na discoidal, they are the predominant form. We have our HDL2, which are larger and richer in lipids and more efficient, and HDL3, which is the opposite of your HDL2. This is the reference range that you will have to be familiar with as medtechs, okay? So the total cholesterol is good if it's between 140 to 200 milligrams per deciliter. HDL, we want it at about 40 to 75. LDL, 50 to 130. And triglycerides at 60 to 150. Okay. So we want this HDL to be quite high, while your LDL and the rest, we want it to be quite low. This is our last slide. It's just showing you which ones are the ApoB containing na lipoproteins. So all of the quote-unquote bad ones have your ApoB. So B for bad. Okay, yan na lang imagine ninyo. B for bad. Okay, and the non-ApoB containing, which is a lot of ApoA instead, is HDL or high density lipoprotein. Okay. Here's the process of what happens. So ayan, your HDL actually takes the excess cholesterol from your cells and puts it back into the liver, while your LDL actually takes cholesterol to the cells. Okay. Your chylomicrons, origin nila is from enterocytes in the liver, and they transport exogenous triacylglycerols or so from diet or somewhere else, not from the liver, from the GIT to your peripheral tissues. VLDL naman, endogenous or those created from the liver to the peripheral tissues. LDL you'll find more in plasma, and they transport cholesterol esters, yung very non-polar version of cholesterols, to peripheral tissues pa rin, while your HDL is the one that controls all of these excessive cholesterols in your cells and transports them back to the liver. Okay? So this was quite a long lecture. I hope you supplement it with other videos that you might want on the internet and read your book. Okay? We'll chiefly be using Harper's, but if you find that it is easier to read other books, you may also do that as well. Okay, thank you so much and have a good day.